Good afternoon, everyone. In previous lecture, we have done even elimination reactions, the stereochemistry of products in even elimination reaction. And today we will proceed with E2 elimination reaction. On what factors the stereochemistry of product depends. So before starting E2 elimination reactions, I will give brief introduction about E1 elimination reaction and what kind of the stereochemistry of the products form in E1 elimination reaction. Then moving to E1 elimination reaction. Yeah. So in E1 elimination reaction, as it is a two-step mechanism, first of all, leaving group is lost, then there is abstraction of H positive. It can be a stereoselective as well as regioselective. Stereoselective means there is predominancy of one product, like trans is more prominent over cis. Trans is formed in major amount as compared to cis. That must be either kinetically favored or thermodynamically favored. Kinetically favored means in which transition states are more stable. That product will be formed in major amount. Thermodynamically stable means when the product formed itself is more stable, then this will proceed via stereoselectivity. Clear? The next one is regioselectivity. Regioselectivity means in particular region a double bond is formed. So in case of E1 elimination, there is formation of highly substituted alkenes. This is according to Jetsev rule. Yeah. So in case of E2 elimination reactions, the mechanism is proceeding through only one step. In this, both the H positive and the leaving group are removed simultaneously, thus formed an alkene. So this alkene may be cis, trans, E or Z configuration. Clear? So what is cis and trans? You already know about cis and trans. Now I will discuss about the configuration E and Z also. So when the same groups are present on same side, like this, CH3, CH3, H, H, clear? Then we will call this cis configuration compound. If the same groups are present on the opposite side, then it is known as the trans form. H, CH3, like CH3 is here, CH3. So there is angle of 180 degree, clear? And here is angle between like 0 to 30 degree, clear? So this is your trans form. And what is E and Z? When we have different groups, it is not necessary that the groups will be same. Like in above mentioned case, there are two methyl groups and two of them are hydrogen. But it is not necessary in all cases that there are methyls and hydrogens also. So let me explain with the example. Chaz, on this side there is a phenyl group and this side methyl group, phenyl group and H. Clear? Okay, then this isomer is also known as trans isomer because in this both the phenyl groups are opposite to each other. Clear? Okay. So when we have to designate E configuration, we designate E configuration in those cases in which there are more than 3 different groups are present. But in this case, 2 of them are similar. There is some another example I am taking, CC. pH, CH3, H, and you can take their bromine. Clear? Okay. So in this case, how will you assign the configuration, whether it is cis or trans? In this case, we will assign the configuration E and Z. E is when high priority groups are present on opposite side of double bond. Okay. So first of all, check the priority. We will give first priority to phenyl group because this is large group. It has large molecular mass. This is carbon number 1 and this is carbon number 2. So with carbon number 1, one phenyl group is attached, another one is methyl group. Let's check these. Clear? And with carbon number 2, one is hydrogen and another one is bromine. So we will give highest priority to the bromine. So highest priority group in this molecule are present in opposite direction. So this molecule is assigned as E configuration. Clear? So taking its another example, C double bond C, pH, CH3, Br, H. So this is carbon number atom 1. This is 2. Check the group attached with the carbon number atom 1. This is your phenyl group and we will give it highest priority. Okay. And we will also check for the carbon number 2. The highest priority is given to the bromine. So the highest priority group are present on the same side. So then it will be assigned as Z configuration. So this is the difference between E, Z, cis and trans configurations. Clear? Hmm. So we were discussing about the alkenes. It may be cis trans or EZ, means R1, R2 may be same or these may be different groups also. Then accordingly, we will assign it cis trans, either E or Z. Clear? Then moving to discussion about the stereochemistry of the product form in E2 mechanism. In E2 mechanism, what kind of products are formed? So first of all, just look at this structure. This is sawhorse structure. Wait a second. Okay. So this is sawhorse projection in which there are, this is methyl group. Here is also methyl group, methyl group, methyl group. Okay. So this solid bond, which is highly filled like this. This is known as wedge. It represents when an atom is present above the plane. Wedge represent when the atom is present above the plane. When this is like this bond, dash bond. Clear? This represent when atom is below the plane. Clear? Okay. So these bonds are like simple plain solid line. Plain solid line represent when the bonds are in same plane. Yeah, such as you can consider like there is a plain paper. Clear? So one of them acts like it's a halogen. It is present in the plane as paper, but another one is methyl. The another one is also methyl. One is present in above the plane and one is present below the plane. Like this is a plane. One is above the plane, another one is below the plane, and the molecule X is in the plane. So these are the bonds which have different representations. Clear? Hmm. For E2 mechanism, there is one necessary condition: the leaving group and the hydrogen to be abstracted. To be abstracted. These should be anti-periplanar. These should be anti-periplanar. So here, what is the meaning of anti-periplanar? Means they should be parallel to each other, but in the opposite directions. Clear? Like this. So look at the example. So in this, you can see these are two methyl groups and halogen and hydrogen. These are parallel to each other, but in opposite directions. Clear? Their lobes are in opposite direction. Here is largest lobe in the upper direction and the largest lobe in lower direction. So these are anti-periplanar. So here H will be abstracted and the leaving group will be removed, thus forming an alkene. The another possibility is when these are present in, these are not in, you can call it periplanar instead of anti-periplanar. When these are in same plane like this, see just the orbitals of halogen and hydrogen, they are present in the same direction like this. So in this, hydrogen is abstracted and the leaving group will be removed. But the possibility due to this conformation is less. So the major product formed will be due to this stereoisomer. It will yield the alkene. So in this case, there is less good arrangement. So this is not good or perfect conformation for the E2 mechanism to be followed. So for the E2 mechanism, the leaving group and hydrogen should be anti-periplanar. Means these should both should be in the opposite directions. Yeah. So if I summarized, in summary, I can say E2 elimination reactions preferentially occurs or take place from anti-periplanar conformation. Just, yeah, one more thing. This is the Sawhorse structure. First one is Sawhorse structure and second one is Newman projection. Newman projection. So we can represent the molecule in both form and we will understand the concept of the formation of product and stereochemistry of product through the Newman projection. We will convert the Sawhorse structure into Newman projection. And how? See, this is carbon number 1 and this is carbon number 2. If you are looking from this side, clear? This is carbon number 1. So just make a dot. This represents your carbon number 1 and it is forming 3 bonds. Okay, so this is a horizontal line. Suppose this is a horizontal line also. Okay, here the solid bond is in the downward side, then draw it in the downward side. Clear? Always draw wedges on the left side, wedges on left side and the dashes on the right hand side. Clear? This is carbon and carbon is attached with 2 methyl group. Here is your hydrogen. Okay. Then draw your, represent your second carbon by plotting a circle. This is little bit wrong. It should be in the center. So I will represent it with another color so that you can distinguish it. Like this. This second carbon is behind the first carbon. If you are seeing from this side, you can't see this carbon. So just I am presenting here a circle. This represents the second carbon. Okay. And the second carbon, this solid line bond is present above the horizontal line. This horizontal line. Okay, then the X will be here. Okay, so I told you, you have to present the wedges on left hand side. So the molecules or atoms present on the wedges will be on the left sides for both carbon, carbon number 1 or carbon number 2. And for here, you will present the bond which is in dash formed, such as I will give number to these 1, 2, 3, 4. Clear? So this is for first carbon, and at the wedge there is one group of atoms. So here will represent 1. And this is the wedge for the second carbon, and for the wedge for the second carbon, the number is 3. So there will be third group. Okay. And this is for the first carbon, and for first carbon at the wedge, it is marked as 2. So here will be second group. And here will be fourth group because it is attached to carbon number 2. So by this, we present our Sahor structure into the Newman projection. Clear? So you can, if you are seeing from this side, from left to right, and I told this situation in case of when you are seeing from right side, means you are watching right to left. When you are seeing left to right, then you can change the direction of wedges and dashes. Like this, you can represent wedges on this side and dashes on this side, and the solid bond, one is above the horizontal line and the below is the below the horizontal line. Clear? So this is the way to present Sahor structure into Newman projection. So just take a look at this structure. In this structure, the hydrogen and leaving group both are at the angle of 180 degree. So this is your anti-periplanar structure. So this is the condition for the E2 reactions. So that this, when the hydrogen is abstracted, the leaving group will be removed like this, and there is formation of a double bond. Clear? So this is your anti-structure. Okay. So the second case in which the halogen and hydrogen are present on the same side. So this is your eclipsed structure. Clear? When they are facing toward each other, like this is something like a stick, and there is something like a stick on the back side of it, but you can't see it. You will see only this further first stick. Clear? So they are like similarly. The case is like these two sticks. So as they are overlapping each other, so this is eclipse structure. As they are opposing each other, this is your anti-structure. So here is the angle between them is 0 degree. Clear? Between hydrogen and halogen. So that's why it is called eclipse structure. Okay. Okay, then let us consider this example. 2-bromobutane. 2-bromobutane, and the base used is sodium ethoxide. It will give two isomers. One is trans, another one is cis. And their total ratio is 81%, but still trans is in major amount as compared to cis. And in minor amount, there is also formation of another isomer that is in remaining is 19%. Clear? How is it possible? We will discuss it in detail. Okay, so here two isomers are forming, trans and cis, as this is the case similar to even reactions. As in even case, it is also giving stereoselective products. where trans was dominating over cis product. So how is it possible in this case also? Let us consider this example. So this is the bromine. Okay, the carbon next to bromine is known as alpha carbon. This is alpha carbon. This is also alpha carbon. Okay, so there is possibility of removal of hydrogen from this carbon also and this carbon also. Clear? Okay. So you can designate the HA, HB. There are two hydrogens and there are three hydrogens. These all are the same. Clear? Here, just draw the Newman projection of this structure. Here, there are two possibilities. It can form two conformations. What kind of two conformation? In which both bromine and hydrogen are anti-periplanar. Clear? So in this hydrogen and bromine, they are present at the 180-degree angle. In this also case, hydrogen and bromine both are present at the 180-degree angle. So both the conformations are possible. So what is the difference between these two conformations? In these conformations, the methyl groups are present also at 180-degree angle and hydrogens are also present at 180-degree angle. But in this case, they are not present at the 180-degree angle. They are present at the 60-degree angle. Clear? So this structure is known as gauche structure. When the groups are present at the 180-degree angle, then structure known as anti. When they are groups present at the 0-degree angle, then the structure known as eclipse structure. When they are present at the 60-degree angle, then the structure is known as either gauche or staggered form. So this is the difference between three different Newman projections. Clear? So this is clearly anti-structure and this is gauche or staggered structure. So I will discuss firstly these two cases, the formation of trans and cis isomer. How is it possible? Either whether the hydrogen is abstracted from this carbon. This carbon has two alpha hydrogen. So the hydrogen can be abstracted from either A position or B position. There are two possibilities. That's why there is formation of trans and cis isomers. You can see here the proton A is anti-periplanar and when proton B is anti-periplanar. What is the difference when proton A is anti-periplanar? These two methyl groups are lying close to each other. So here it is causing steric hindrance. So gauche is less stable configuration as compared to anti-structure. In this, methyl groups are present at the opposite side. And in this case, the proton B is abstracted. So due to the possibility of abstraction of two different protons, HA and HB, it led to formation of two configuration in which there are the hydrogen and bromine are present opposite to each other at the 180-degree angle. So antiform is more stable than the gauche form because there is less steric hindrance in the antiform. So that's why it led to the formation of a major product that is trans. And simultaneously, it is also providing a product that is known as cis product, but it is found in the minor amount as compared to trans. So because of the less stability of this gauche conformation. Yeah. So the next possibility, third, when the hydrogen is abstracted from this carbon. Okay. So this is also formed in 19%. So this is in minor amount. If we are discussing about this, because these are in the major amount, trans and cis, when both trans and cis are formed and trans is dominating cis, then for that we use the term stereoselectivity. Stereoselective. Clear? So whatever the stereochemistry of the reactant is, but it give a product in dominating amount. Here one is more dominating than other. So for that we will use the term stereoselectivity. So E2 reactions can be stereoselective as E1, but their mechanism is different. As you know, I have already discussed the mechanism with you guys. So because of there is a choice of two hydrogens can be abstracted from the alpha carbon. That's why here E2 is stereoselective in nature. Clear? Okay. The second case is when the E2 reactions can be stereospecific. Clear? So there is a difference between stereospecific and stereoselective. Stereoselective, whatever is the stereochemistry of reactant, it will give one product predominating over another product. Clear? We have discussed already this. So in case of stereospecific, so it depends upon the stereochemistry of reactant. Whatever the stereochemistry of reactant have, it will give the product similar to the stereochemistry of reactant as it have. So look at the definition of stereospecific. Clear? Stereospecific. So it led to the production of a single isomer as a direct result of mechanism of reaction. It will give single isomer as a direct result of mechanism of reaction and the stereochemistry of this starting material. Because there is a no choice, it gives a different diastereomer of product from each stereoisomer. If you have reactant A, it will give the product B. If you have reactant C, it will give the product D. And this is not possible here, like if A is giving two kind of product, B plus D. This is not possible. Only this is true in case of stereospecific. So let us clear this point more by discussing the example how the E2 can be a stereospecific. Clear? So look at this example in which there are two carbon, 1, 2, and carbon number 1, it bears two groups. One is bromine, another one is phenyl, and the third one is hydrogen. And carbon number 2, it is also bearing a methyl group, phenyl group, and at the wedge is a hydrogen group. Clear? So if we redraw this structure, I will let you why we redraw this structure. So, but on later. But first of all, understand the concept of this. Clear? So I have a reactant over here in which methyl group is above the plane and bromine is also above the plane. So what kind of product we will get? Clear? I will just draw a rough mechanism of it so that you can understand the concept. This methyl group, phenyl group, hydrogen group, and the bromine group at the second carbon, and then hydrogen at here, and here is the phenyl group. Clear? So this hydrogen should be abstracted and the bromine will be lost. Clear? So there is formation of an alkene. There are two possibilities. The possibility is that this phenyl group can be in same direction or in opposite direction. The another possibility is like this, in which phenyl groups are in same direction. When both the phenyl group are in same direction, in same phase, this is known as Z alkene. And this is E. In this, both the phenyl group are present in opposite direction. So that's why we are calling it E alkene. But in this case, in this stereoisomer only, the product form is E alkene. There is no formation of Z alkene. So why the Z alkene? We do not obtain any kind of Z alkene because this reaction is stereospecific. In case of stereospecific reaction, we only get the one particular alkene, either Z or E alkene. Okay, so I have read, just wait a second. You can see this here. The hydrogen and bromine, these are not periplanar to each other. So the condition for the E2 mechanism should be anti-periplanar. So first of all, we have to convert this structure into the anti-periplanar structure. So to convert anti-periplanar structure, we have redrawn this structure. I will make you understand this structure through the Newman projection structure, but just first of all, focus on this substrate after redrawing. Clear? In this case, this hydrogen and bromine both are the anti-periplanar to each other. Clear? So hydrogen will be abstracted from here and the bromine will be closed. Clear? If I draw the Newman projection of this substrate, then what will be the structure? So this is your carbon number 1. Carbon number 1. Clear? This is your carbon number 1, and the bromine is present above the horizontal line. So it is mentioned above the horizontal line. So in the upper side, clear? And it is attached with two groups. One is phenyl, another one is hydrogen. Phenyl. So dash bonds are presented on the left hand side here and wedges are presented on the right hand side. So hydrogen on this side and the dashes on this side. Clear? And this circle represents a second carbon, and with second carbon, one is methyl, phenyl, and hydrogen. Then just check the solid line below this horizontal line, it is hydrogen. So draw hydrogen opposite to this bromine group. Clear? Then just a second. I need to connect my charger. Okay. Yeah. So let's see what is the group on for the second atom on the dash, that is methyl. So I have drawn on this side. And what is the group on the wedge, that is phenyl. So draw just the phenyl group over here that is connected to carbon number 2. As we cannot see carbon number 2 clearly, so that's why this is drawn in the form of a circle and the carbon number 1 is in the form of a dot. So both the groups are anti-periplanar to each other, hydrogen and bromine. When hydrogen is removed and hydrogen is abstracted and bromine will be removed, then there is formation of a alkene. You can see in this both the phenyl groups are opposite to each other. That's why it is giving E alkene. Clear? So this is the theory behind the formation of E alkene over here. You have to draw the structure in which both hydrogen and bromine are anti-periplanar to each other. When you draw the sawhorse structure, then convert that structure into the Newman projection. Then after the elimination of leaving groups and hydrogen, just draw the stereochemistry of the product, that is E alkene in this case. Yeah. So same is true in the second case. So just see the difference between these two substrate. In this substrate, the methyl is below the plane and bromine is above the plane. So these both are the diastereomers. Clear? Diastereomers are those molecules which have same number of groups, but they do not form any kind of mirror images of each other. Clear? So those groups are known as diastereomers. So this stereoisomer is different from this. So of course, as it is different, it will give different kind of alkene, as it is giving Z alkene in this case. And why it is giving Z alkene? Because this is not clear from the substrate structure. You need to draw to the Sawhorse structure, then convert it into the Newman projection. Then further you can identify the product here. So this is the Sawhorse structure for this molecule in which both hydrogen and bromine are anti-periplanar to each other. So when these two groups are removed, so just look at this Newman projection. how this is Newman projection. This is carbon number 1 and bromine is above this horizontal line. So drawn it in the upward direction and these hydrogen and phenyl groups. Okay. In this case, dashed are on left hand side. In this case also, dashed groups are on the left hand side. So phenyl is on the left hand side. And this hydrogen that is on wedge, that is on the right hand side. Then this is your second atom, carbon. Clear? So carbon is linked to phenyl, methyl, and hydrogen. So dashed group is present on the left hand side as in case of second carbon also. And this methyl is group present on the right hand side. This is also true in the case of this case. Clear? And the hydrogen, it is a solid line. It is, we will represent it in the downward direction because it is below the line. So like this, I have drawn its Newman projection structure. So when this group is removed, so in this, both the phenyl groups are very close to each other. So they are like this. So that's why it is forming Z alkene or Z alkene. So this is the chemistry behind why E2 reactions also give stereospecific products. And this is only possible when there is one possibility of abstraction of H positive. Clear? Because this carbon has also one hydrogen, this carbon has also one hydrogen. That's why there is only possibility of abstraction of only one hydrogen. In previous case, there was the possibility of abstraction of two hydrogen. So it was giving stereoselective product like this, trans and cis. Clear? This is trans and cis. So let me explain how I have redrawn this structure converted into this. That is the important point. Because if you are shifting the groups, then you have to shift all the groups together. Clear? Like see in this structure, bromine is at the wedge position. If here bromine is the wedge position, then when you will redraw it, then it must be on solid line because as this on solid line and this should be wedge. The remaining hydrogen should be then on wedge. Clear? Okay. So if you can interchange the groups also here. Here methyl is on wedge. It should be on dotted line. And it is on solid line. Then it should be on wedge. And hydrogen should be a solid line. But how we have redrawn this, I will make you understand this Newman projection. First of all, this is carbon number 1 and this is carbon number 2. For the carbon number 1, draw a dot and okay. So phenyl group. This is a solid line and it is in upward direction above the horizontal line. Clear? Okay. Then dashed we are representing on left hand side and wedges we are representing it on right hand side. And what is present on the wedge? That is hydrogen. And what is present on the, sorry, dash line? That is hydrogen. And on the wedge, that is bromine. And draw for the second carbon also. For the second carbon, what is below this horizontal line? Phenyl group again. Okay. Then dash line, that is hydrogen. And on the wedge, there is methyl group. Yeah. Wedge, there is methyl group. And okay, that's clear. This is a clear structure. Okay. So our condition is for the E2 elimination reaction, the hydrogen and bromine should be anti-periplanar, means bromine or hydrogen. Both should be in upward or lower direction, upward or downward direction. So, but in this case, bromine and hydrogens are not present in upward or downward direction. So, this is your upward direction, which represents the solid line. This is your downward direction, which also represents the solid line. These two represents the wedges, and these two represents your dashes. Just wait. This is carbon number 1. Bromine is present at the wedge, right? Here, wedge. Methyl for the second carbon is at wedge. So here will be the hydrogen. Hydrogens, both the hydrogen are present in dashes. So it is represented on the left hand side. Clear? So these hydrogen and bromine, these are not present at the solid line. That should be upward and downward direction. So we have to convert this into upward direction. Clear? So for this, we will rotate this carbon. As this bond is sigma bond, it can be rotate freely. So just rotate from here. When it rotate from one side, what happen? Shift, these groups will be also rotated because these are fixed like a shaft, such as this. Three groups are attached to this carbon. When you will rotate this, what will happen? Like this is 1, 2, 3. They will interchange their position. Like 1 will come here, 2 here, and 3 will come here, like this. So upon interchanging their position, what will happen? I'm changing only the group of carbon number 1. So just again draw the structure after interchanging the position of the groups. After interchanging the position for carbon number 1, bromine at this position, and this phenyl will be at this position, and this hydrogen will take will take the place of bromine, like, and this will be the structure like this, and the carbon at the back side will remain same, because when you will rotate a bond from one side should be a fixed like a shaft, like it is fixed with something. If you are rotating it, then there is some fixed point here. So the bonds for the remaining your back carbon are would be at the same position. So these are in the blue line to just these are groups for the second atom. Okay. Again, what is anti to bromine? That is a phenyl group. So for this, we have to next again rotate at the 60-degree angle. So it was the rotation at the 60-degree angle. So again, rotate the groups at the 60-degree angle, but now for the carbon number 2nd. So now fix the carbon number 1 and rotate this. For this, the group will interchange their position. So what will happen for carbon number 2? Carbon number 2, this hydrogen will take the position of phenyl group. Just a sec. So hydrogen will be over there, and this phenyl will take the position of this methyl group, and this methyl will take the position of this hydrogen, because we are rotating it at 60-degree angle. Again, draw the groups for the first carbon as it, because we have fixed the position of first carbon, hydrogen, phenyl. Okay. Now, these two are anti-perilinear to each other. So this is a perfect Newman projection for the removal of leaving group and abstraction of hydrogen. So in this, both the phenyl groups are trans to each other. So you can look at the structure we have already discussed, in which both the phenyl groups are opposite to each other. And we have drawn the sawhorse structure for this. And for this sawhorse structure, so as this is a wedge, phenyl is at the, sorry, just a sec. Yeah, at this side we have, this is for the wedge, so hydrogen is at the wedge, okay, and phenyl is wedge for the second carbon also, and methyl is at the dash position for the second carbon, and here phenyl is the at the dash position for the first carbon also. There is the groups which are present at the dash bond. Clear? So by this we can convert Newman projection into sawhorse as well sawhorse into Newman projection. So you can redraw directly it from the substrate starting material, but the good thing is you can draw through Newman projection. This is a perfect way because there is the possibility of imperfection decreases in this case. Clear? So I will suggest you to go through these all structures rather than drawing direct this structure. Clear? So similarly, you can draw in the case of this isomer also, this one, and I will let you know in this case also to clarify you so that there will be no doubt. Phenyl ring in the, this is carbon 1, carbon 2, phenyl ring in upward direction. Okay. And bromine at the wedge. Okay. Then hydrogen, then of course it will be at the dash position. And for the second carbon wedge, here hydrogen is at wedge. Okay, then here wedge. On this side, dash. And the methyl is at the dash position. Clear? So phenyl, this is below this horizontal line. So this is at the lower position. Yeah, one thing is more. In Newman projection, we don't represent here like wedge or dashes. We just represent in the solid lines here. Okay, so because there is no rule, there is no need to represent here wedge or dashes. This is the point you have to keep in the mind how to represent these dashes and wedges around these two carbons. Clear? By keeping this point in mind, okay. Then again, the bromine and hydrogen, these are not anti-periplanar in this case. So what we need first, rotate this so that this can be in anti-periplanar position. Just rotate the first carbon by fixing second one. So when you will do like this, what will happen? Bromine, hydrogen, and phenyl group, and second carbon was fixed. So methyl, okay, that are rotated at 60 degree in anticlockwise direction. Clear? Okay, so now the hydrogen of second carbon and bromine should be anti-periplanar. So this must be at this position. So again, rotate it in clockwise direction at 60-degree angle. Then you will get bromine. So first is fixed. First carbon is fixed. In case of second, hydrogen over here, phenyl here, methyl here. Okay, then hydrogen will be removed and then bromine will be removed. You can look at this structure. Both the phenyl groups are close to each other. So you will get in this case Z alkene, either Z alkene. Clear? So this is a theory behind why you are getting stereospecific products. Clear? Okay. Then moving to next example. So this was the case in case of simple saturated alkanes. When if you have any alkane which is cyclic in nature, so what will be happen in case of a cyclic like this? I have a cyclohexane, chlorocyclohexane. So these two are similar structures. So X here is halogen. That may be chlorine, bromine, iodine, any of these. Clear? So in case of cyclohexane, the condition is same. In this also, the hydrogen and halogen both should be anti-periplanar to each other. So for the antiplanar, both should be present at the axial position. So here it is present at the equator, halogen. Okay. So here is the hydrogen that is at the axial position. Clear? But for the removal of these two groups for the E2 elimination, you have to follow the condition of anti-periplanarity. So for this, we will flip the structure. We have flipped the ring, inverted the ring. You can see now X is at this position. This is carbon number 1, this is 2. Now this is carbon number 1 and this is carbon number 2. We have just invert the ring. So just check how many carbons, adjacent carbons, are parallel to this hydrogens. Sorry, uh, how many how many hydrogens are parallel to this halogen group? 1 and 2. So there is a possibility of removal of two hydrogen because these both are the alpha position. Hydrogen either can be removed from this or this. It will get only one isomer because there are no substituent present on this cyclohexane ring. If there was presence of substitution, then it will be considered that what kind of possibility is there formation of any kind of product, whether it is regioselective in nature or not. So the condition for the cyclohexane is both should be present at the axial position. For this, you have to flip the ring, invert the ring to attain the axial position. Okay, then let's discuss it with an example. So this is your cyclohexyl ring. Okay, then at first position, second, third, fourth, fifth. Sixth position. So these groups are attached here. Clear? So this is the alpha position next to halogen. This is also alpha position next to halogen. Here, there are two possibilities. Hydrogen can be abstracted from here. Okay, and hydrogen can be abstracted from here, from second position as well also. So there is formation of two product. If the hydrogen is abstracted from this carbon, then the first product will be formed. If the hydrogen is abstracted from this carbon, then the second kind of product is formed. As the base here we are using is less strong, but less hindered, not bulky as base used like this NaOC butyl groups. When we use butyl groups over here, 1, 2, 3, 4, that is more bulky as compared to ethyl groups. Clear? So but ethyl groups are less bulky in nature, so it is not causing any kind of steric hindrance from here. Then it will give a stereoselective product, the product which is stereoselective, because here the base is not bulky as tertiary butyl oxide, CH3, CH3, CH3O. Here you can take also sodium. This is tert butyl oxide. Clear? So it has simple structure Na positive O 1, 2. So there is only 2 carbon in ethyl. So this is 2 carbon bond. 1, 2. 1 carbon, 2 carbon. So this is the way. This is not bulky. So as it is not bulky, it will follow the rules as for E1 elimination reaction. It will give highly substituted product in major amount as the ratio is 1:3. Let's look at this example. And this carbon, this carbon is attached to one alkyl group. This carbon is also attached to one alkyl group. So this is disubstituted alkene. But in this case, this carbon is attached to one alkyl group, and this is your another alkyl group. Two carbons, and this carbon further is connected to one alkyl group. So 2 plus 1, 3. So this is tri-substituted. So here tri-substituted alkene will be the major product. So regioselectivity you have to check also the based on the what kind of base you have been using in E2 elimination reaction. Less substituted product can also be the measure, but you have to check what kind of base we have been using, whether it is bulky or not. Clear? So in this, we have changed the stereochemistry of this product. In this case, the stereochemistry of chlorine is different. And you see, this reaction is 250 times slower than this. And in this, we will get only one kind of product. And the reaction is slower. Why? Let's discuss this example. What kind of product we have been getting here and why this reaction is slower as compared to this upon changing the stereochemistry. So what is the effect of change in the stereochemistry of this reactant? Uh, just a second. In this case, this is your A case. Yeah. In A case, what is happening? This isopropyl group, carbon 1, 2, 3. These are in the branched form. So this is your isopropyl group. This is your methyl group. These two are present at the axial position, and this chlorine is present at the equatorial position. Clear? This is at the equatorial position. But for the elimination, what is the rule? The leaving group and the hydrogen should be anti-periplanar. Hydrogen here is at the axial position. It is at the equatorial. So you need to convert the ring inversion. So when you go for the ring inversion, when the inversion is done, the chlorine will take the axial position. Clear? And this hydrogen also have axial position also. The hydrogen adjacent to this chlorine. There are two hydrogen adjacent to this chlorine. This is 1 and this is 2. And this is the carbon hydrogen 1 and this is the 2. Both are parallel, anti-parallel to chlorine. Clear? So the hydrogen can be removed from here and the hydrogen can be abstracted from here. So that's why there are two possibilities. There are formation of two different products, but the product which is highly substituted, more substituted, is found in major amount. Clear? One thing is more, you will see here, this conformation is more stable than this one. Because in this case, the bulky group like methyl and isopropyl are present at the equatorial position. But in case they are present at the axial position. In case of cyclohexyl, if bulky groups are present in equatorial position, then that is considered as more stable rather than if they are present at the axial position. You have to keep this in the mind. So that's why just see this arrow. This is larger in this direction, means the direction is shifting towards this forward direction more easily, because this is more stable state. In backward direction, it is less possibility to convert this into back axial position. The possibility in forward direction is more because of the stability of this ring. Clear? The reason behind is that the bulky group at the equatorial positions are more stable due to low diaxial steric hindrance, because there can be axial interaction between these two groups, 1, 2, 3, 1, 3 diaxial interaction. So here, okay. Now consider the second case. This is your B case. In this, what is happening? In the previous case, chlorine was present in the equatorial position and the isopropyl and methyl. These are present at the axial, and chlorine at the equatorial. But in second case, what is happening? All the groups are present at the equatorial position. Okay, now check the hydrogens, carbon-hydrogen bond parallel to this chlorine. There is no carbon-hydrogen bond. There is a carbon-carbon bond parallel to this chlorine, this one and this one. There are two bonds which are parallel to this carbon-chlorine bond. So there is no CH bonds. That's why there is no elimination reaction in this. But if the ring is inversion, if there is inversion in the ring, so what is happening? There is bond axial. There is one axial bond that is CH, and that is anti-periplanar to CCl, and this will be removed. Here it is, the hydrogen bond is at equatorial position. There is one axial bond. That's why in this case, the possibility of one product, that is where the double bond is present over here. Clear? So when we draw shear conformation of this substituted cyclohexyl group, in this case, all are present at the equatorial position. So this is more stable as compared to this. In this, isopropyl and methyl groups are present at the axial position. So steric hindrance in this shear form are more as compared to this. So the ring inversion in forward direction is less, but in backward direction is up to more extent. That's why. So there is possibility of this production in low concentration because this ring inverted is in low concentration because the reaction is not proceeding in forward direction. The ring is not flipping in forward direction. As this concentration of this species is low, of course, again, the product form will be also very slowly. That is in also found in low concentration. So that's why this reaction is 250 times slower than the previous one because of the presence of this bulky groups. So this isopropyl group has preferential effect on the formation of product and the stereochemistry of the product. So this was the case of cyclohexyl groups. In case of cyclohexyl group, the leaving group and the hydrogen both should be present at the axial position. Clear? Okay. So that was in the case of cyclohexyl. We have also discussed saturated alkanes also. So in summary, we can say E2 reaction can be stereoselective as well as stereospecific. Stereospecific when there is possibility of only abstraction of one hydrogen, beta hydrogen. When there are two beta hydrogens at, okay, so in that case, it will give stereoselective product. Otherwise, it will give stereospecific product, either E or Z. So we have discussed this in detail as well in the case of cyclohexyl groups. So next is our question about regioselectivity. Clear? So for regioselectivity, I have already told you it also depends upon the what kind of base we have been using. Just look at this example. In this example, our initial reactant is this, that is 1, 2, 3, 4. 2 bromo, 2 methyl butane. This is our initial reaction, and it was subjected to undergo E2 elimination reaction in the presence of tertiary butoxide, and here is the sodium ethoxide. As we know, tertiary butoxide is a bulky base. Bulky base, there is a steric hindrance in it. So due to steric hindrance, clear, it will prefer to abstract the proton from less steric hindered side. So it will abstract proton from here and give us less substituted product in major amount. Clear? And we are also getting the more substituted product in some amount, that is about 28%, and less substituted product in the major amount. One thing is, what is the reason behind this? Clear? So why the possibility from abstraction of proton in case of bulky base is less? Just look, if yeah, I will discuss some other in next example. So what is the reason behind? I will discuss it another example. So here is the case of the base. In case if the base is bulky, then it will give less substituted product in the major amount. Here, okay. So now here is the sodium ethoxide. Base is not bulky, so more substituted product in major amount, less substituted in lower amount. So this is the case of regioselectivity. So it depends upon the what kind of base we have been using. Okay. So next is the case when we have been using bulky leaving groups such as quaternary ammonium. Quaternary ammonium. You can take another example. Instead of bromine, you have been using quaternary ammonium and positive ET3. So here nitrogen has four bonds. That's why we have been calling it quaternary nitrogen. Okay, and the base we have been simply using sodium ethoxide. Clear? It is still giving us less substituted product in the major amount. Here the base we have been using is simple, not bulky. But what is the difference on the leaving group? Here the leaving group is bulky. In this case also, we will get the less substituted product in the measured amount. So what is the reason here? As there is no difference in the base if the hydrogen is abstracted from A position and abstracted from B position. Look for both conditions. In condition A, just substitute it more. H. Let me draw again this example. H, Br, CH3. Okay. This is your alpha carbon, and this is here is also alpha carbon. Clear? But you need to take it. Again, wrong structure I have drawn. Sorry for that. H and positive ET3 CS3. Okay, this is alpha hydrogen. This is also alpha hydrogen. Okay. If the alpha hydrogen is abstracted from A position and B position, let's discuss the both. This is for B and this is for A. Okay, when abstracted from this position, clear? H and 83 positive. Okay, H positive. Clear? Similarly, you will draw for the second case N positive 83. So here is the positive charge. CH2 here, CH3, sorry. So here there is steric hindrance over here also. That's why that is the one of the reason in this case we will get less substituted product. Clear? So this is a major reason there is electrostatic repulsion between these two charges. As well, this hydrogen is less acidic as compared to this hydrogen. The second reason is this. This hydrogen is less acidic because these two methyl groups have plus side effect, means these will provide shift the electron towards this carbon through the sigma bond. Either it can form hyperconjugative structure. Hyperconjugative structure by forming no bond between carbon and hydrogen. So here it can also form a double bond by forming hyperconjugative structure. So in both cases, it increases the electron density on this carbon. If it is increasing electron density on this carbon, then it is difficult to abstract here the H positive because this carbon is already have more electron density. If it has more electron density, it will not bear any kind of negative charge again. Otherwise, it will feel destable due to more negative charge. So this is the reason here. So there are two reasons. This hydrogen is less acidic. Clear? Second one is so this is a major reason. So here will be the negative charge. Sorry. So this is a major reason why the abstraction of hydrogen from here is less possible. There is lowest possible in case of A, and in case of B, there is more possibility. Clear? So one is the if we have been using strong or bulky base, which is causing steric hindrance. The second is the case when we have been using the substrate in which one end is more substituted as compared to another. In that, and the leaving group is quaternary ammonium. In that case, we will also get the less substituted product in the major amount. So these are the cases. Clear? So this is for regioselectivity. Let's discuss some another example. This is methyl cyclohexanol, and it was subjected to undergo even reaction in the presence of acid. So we have discussed already in case of E1, if the as OH is a bad leaving group, it do not undergo E2 elimination reaction upon protonation only. It is possible. It undergo even elimination reaction as this reaction is carried out in the presence of acid. So first of all, this OH will get protonated to form OH2 positive. Then here there will be formation of a carbocation, tertiary carbocation like this. This here the carbocation formed will be tertiary. 1, 2, 3. This is attached to 3 alkyl groups. That's why we have been calling it tertiary carbocation. Further, the hydrogen will be abstracted either from here or from here. Both will form the same product. So this is only case in the possible of even reaction. Okay, now we have substituted the OH group with chlorine group. We have changed the leaving group as well as the conditions also. So we have been using more steric hindered base so that it can undergo E2 reaction. But E2 reactions proceed in one step. So first of all, what is the structure of this base? 1, 2, 1, 2. And K positive. Triethyl. 3 groups are attached to this carbon. Okay, so in this case, what kind of product we have been obtaining? In this case, we have been obtaining the product which is less substituted, which is less substituted. But in this case, we are getting highly substituted. Clear? Because this is clear because OH is not a good leaving group. Here we have changed the leaving group. But in case of chlorine, but chlorine is a good leaving group as compared to OH, but still we are getting less substituted product. So that why? So for this, for the E2 mechanism, just always remember the both leaving group and H positive should be anti-periplanar, but this is not necessary condition in case of E1. That's why we are getting highly substituted. So I have just drawn its chair form. Okay. So chlorine is present at the axial position and methyl is at equatorial position. And these two hydrogens, adjacent hydrogens, which are anti-periplanar to chlorine. These are two hydrogens. Okay. Hmm. So there is possibility number one, possibility number two. There are two possibilities. Clear? Okay. The hydrogen will be abstracted from that case in which there is less steric hindrance. But in this case, the ring is more hindered, because chlorine is present at the axial position and the methyl is present at the equatorial position. So it is difficult to abstract the position from these two positions, these two alpha hydrogen. So it will abstract the hydrogen from this methyl group. This is the another shear form where I have only drawn this methyl group in the expanded form, and I have mentioned the hydrogen which is parallel to this CCl bond. Both are axial in position, so anti-periplanar to each other. So there is formation of a double bond. That is less substituted alkene is formed. Clear? So as the base is sterically hindered, so it will not abstract the protons from here. It will prefer to abstracts a proton which is less hindered. Clear? So this is all about regioselectivity. If I summarize both things, stereochemistry, E2 can be stereoselective as well as stereospecific. Regioselective, it can also give highly substituted product. It depends upon the type of base, and as well less substituted product. Clear? So in this case, both these situations are possible: stereoselective, stereospecific, highly substituted, and less substituted. And moreover, when we get less substituted alkenes, that rule is known as Hoffman rule. And Hoffman has given this rule, like if the alkene is highly substituted, then that is Zetsov rule. When we get less substituted alkene, that is Hoffman rule. So this is the difference between these two rules. So by covering this, we are completed with our topic E2 elimination reactions. And then in next lecture, we will discuss more examples of E2 and E1 eliminations so that we can go for the MCQs so that we can solve them easily. Thank you. Please share and subscribe my channel. And if you have any query, then you can ask any kind of question from me and at any time. Thank you.